Welcome. I'm Licia Verde from the Institute of Science of the Cosmos of the University of Barcelona. In this video, I will talk about precision cosmology and blind watchers of the sky. If the title doesn't sound too new, it's because it's similar to the title of a popular book by Rocky Kolb, the same Kolb as the Kolber-Turner, but different book. So any cosmology talk needs to start with something like this about the extremely successful standard cosmological model that with only few parameters can fit all sorts of observations about the universe across different epochs, and the fact that cosmology has entered the precision era. Let's think a little bit deeper about that. Cosmology is special because we can't make experiments despite what we tell the funding agencies, but only observations. We have to use the entire universe as a detector, but the detector is given and we can't tinker with it. So let's think, for example, how we try and we do constrain the sum of neutrino masses by looking up the sky. We are using the entire universe as a detector. This has driven a massive experimental effort of observing as much as possible of the universe. This is a little bit of a mixed blessing. There is what I call the curse of cosmology, because we only have one observable universe, we can only make observation and only of the observable universe and not experimenters. We fit models, that is, constrain numerical value of parameters to the observation. Hence, any statement, or almost any statement, is model dependent. There are also complex astrophysics that is poorly understood and hard to model that comes into the way, and non-linearity. But this is also a blessing because in principle, we can observe all there is to see. And this brings up the idea of the ultimate survey. Once you've observed all there is to see, there's no point in observing it again. It will not help reduce your error bars. And one example of this ultimate survey is here. It's the extremely successful legacy of the Planck mission, because the primary temperature anisotropy of the cosmic microwave background basically has been observed, and the information content has been saturated. Of course, there's much more that can be learned from the cosmic microwave background, and other speakers will talk about that. When we come to large scale structure, and in particular galaxy redshift survey, I like to show this slide courtesy of David Schlegel. There is a sort of Moore's law of galaxy redshift survey, where redshift survey increase by a factor of 10 every 10 years. So if we extrapolate this law, all linear modes will be mapped by 2043, and all detectable galaxies will be mapped by 2061. And in this plot, there is a succession of galaxy redshift survey, which I'm sure you've all heard mentioning, and a forthcoming one, which is called DESI, which will see up to 30 million galaxies. So let me spend a few words to tell you more about the Dark Energy Spectroscopic Survey, or DESI. You can find more at that website. It's an international collaboration, and again, please look at the website to find out all the institutions that are involved. But in a nutshell, it will be done in the Mayall 4-meter telescope at Kitt Peak. Is a stage for dark energy measurement. It'll concentrate on baryon acoustic oscillation, but also much more. About 25 million spectra over 11 billion years of cosmic history, 14,000 square degrees of the sky, tracing galaxy up to redshift 1.7, and then quasars between redshift 2.1 and 3.5. So there's a lot of physical information that can be gleaned by looking at large scale structure. From the clustering information like constituent of matter, physics of inflation, neutrino masses, primordial power spectrum, nature of dark matter, etc. From the baryon acoustic oscillation, from geometrical measurement of the standard ruler, we can learn about the expansion history of the universe, and therefore dark energy, and from Redshift space distortions about the growth of structure and the nature of GR. And all this help us understanding cosmic acceleration. At the larger scales, the information about homogeneity and non-Gaussianity. The data set is much richer than an image like this shows because each point has rich spectral information, and the spectral analysis can give other non-cosmological information, which may be the key, however, to ensure robustness of all the above. So if you have been living in a cave for the past 20 years or so, let me run quickly through what it means, baryon acoustic oscillations. Like in the cosmic microwave background, we have seen the acoustic peaks of that radiation because we observe photons. Photons were coupled to baryon, so the oscillation in these photon baryon fluids are also in the baryon. When we look at the larger scale structure, we actually see galaxy form on the scaffolding given by the dark matter. But as baryons are about 1/6 of the dark matter, this baryonic oscillation leave some imprint in the dark matter distribution and hence the galaxy distribution, and gravity is the coupling there. So in baryonic acoustic oscillations, we have a standard ruler. For the cosmic microwave background, that standard ruler is the sound horizon recombination. For the large scale structure, this is the sound horizon at a radiation drag, but the two are very, very well linked to one another based on simple, well understood physics. So here's the standard ruler. The physics is that sound waves in the early universe propagate until radiation and matter decouple, and this gives us the standard ruler. And this key observable is useful for determining the geometry of the universe as a function of redshift and dark energy equation of state or modification of GR. Well, the early universe physics, which is well known, sets it. Cosmic microwave background observation and early universe physics in a lambda CDM model constrain the standard ruler length to 0.2% precision. So that's precision cosmology for you. So when it comes to large scale structure, I have to introduce also the concept of the Alko-Paczynski effect on a standard ruler. So the standard ruler can be observed not just on the plane of the sky, like for the cosmic microwave background, but also along the line of sight. And on the left-hand side are plot taken from the latest release of the eBOS galaxy survey. On the left-hand side is the correlation function, and the right-hand side is the power spectrum, so the corresponding Fourier counterpart of this acoustic oscillation. And the slide and the image in the middle show you that, of course, you can determine across the line of sight and along the line of sight an incorrect assumption about cosmology, distances, give anisotropic distortion. In fact, all one measures are redshift and angles. In order to convert redshift and angle in distances, an underlying cosmology must be assumed, so distances must be assumed, and this will be important for later. This brings us to the natural variable that appears in most baryon acoustic oscillation analysis, which are the so-called alpha parallel and alpha perpendicular, which are how this standard ruler appears along the line of sight and across the line of sight. And here I also report in detail how this enters in the power spectrum template. There's not just that, there are also redshift space distortion that are linked to the growth of structure. Peculiar velocity, deviation from the Hubble flow, distort the galaxy map along the line of sight. This may seem like a complication, but they are sourced by gravity and the total matter, and there's a lot of useful cosmological information in there. So in this plot, it's a simulation. On the left-hand side, it's a simulation of the real space, and the right-hand side is how that will appear when redshift are transformed into distances. So you see the effect of the redshift space distortions. In the linear regime, this is driven by the linear growth rate of structure, which is related to the omega matter parameter to a certain power gamma, which power depends on gravity and changes a little bit if you have a model of dark energy. The other important ingredient that I want to introduce here is the idea of reconstruction, a sort of time machine. So overdensities drive both linear and nonlinear evolution. And once I get a galaxy redshift survey, I've mapped the overdensity, albeit in redshift space. So this is an image from a nice simulation that Nihil Padmanabhan has done to illustrate the idea of reconstruction. So let's show what the signal from this standard ruler, the statistical clustering signal, will look like at the beginning of a simulation, and then it let the particle evolve under gravity, and in the inset there is the profile of this signal. And as this evolves with time, one can see that that circle get a little bit fuzzed out. And so one loses information about how to reconstruct that standard ruler. But it turns out that the survey has mapped the overdensities. And in the overdensity, one can reconstruct from that, at least in linear or mildly nonlinear regime, a displacement. And this is done here. And then this displacement can be done backward, applied backward to the galaxies or particle observed to slightly undo this nonlinear evolution. And this helps a lot sharpening the baryonic peaks. So let's go back to this, and I hope it is clear that with enough data and enough understanding of the modeling behind this data, we can do precision tests of fundamental physics with cosmological data. But we should always beware of spherical chaos, and I always remind this sentence by Richard Feynman that you must not fool yourself, and you are the easiest person to fool. So here is a good way to introduce this work, Blind Observers of the Sky. And I would like to highlight here the effort of graduate student Samuel Bryden and postdoc Ethel Jill Marin. So the idea is to blind, and I'm sure other speakers in this meeting will talk about blinding. It's a key procedure to remove confirmation bias that has been an integral part of data analysis in many research areas. So many research areas could be called early adopters. Blinding is slowly becoming standard for cosmological survey, as we have seen in the ES, KIDS, in Type 1a supernova, in LIGO, etc. But for large scale structure and especially galaxy lashes survey, this hasn't happened yet. So in the same language of early adopter, we are a little bit the laggards. There are several ways to blind in large scale structure in principle, but few have actually been applied. Some classic technique like salting, which is typically applied to supernovae or gravitational waves, is not applicable. One could apply it at the summary statistic level, and I'm sure we'll discuss about that, at the inference level, hiding the data among a set of mock data set. But what about at the catalog level itself? So in large scale structure, a priori, catalog level blinding allow for infinite freedom to modify the field. You can even write your own signature if you want on there, but that's not particularly useful to blind for cosmology. So what do we want? Before we go on, let's review very briefly how the standard analysis actually works for galaxy redshift survey. The data are taken, the spectra, they go through the redshift pipeline, raw catalogs are generated, then some systematic weight pipeline is run, and then the full catalog is produced. On the full catalog, just a few checks can be done, but there's nothing to protect you from doing these checks with an eye on their cosmology performance. If things are not okay, one can go back and keep iterating. Once things look okay, this catalog gets made available to the collaboration does the analysis. And again, if everything looks okay, and sometimes this okay requires some connection to cosmology and inference of cosmological parameters. So if it's not okay, then one goes back and redo this part and keep cycling until things are okay. And then one look at the cosmological results, write a paper, etc., etc. But as you can see, this internal checking of the pipeline is not completely disentangled from the cosmological inference. And that's where we want to break the cycle. So what's the idea? What do we want? Well, we want to leave this part exactly the same, but do any checks in a non-cosmology performance way. And then once things are okay, run them through a blind box. This blind box is generated, the catalyst data are blinded using a random seed. The random seed then gets hidden. Once everything is okay, it's become available to the collaboration, but the cosmology is hidden and blind cosmological results are found. And then this can be analyzed. If they are not okay, one can always go back and then blind again. The moment they are deemed okay, then we can unblind, so we know what the random seed is, get unblind clustering catalog and unblind cosmological results and write the papers. Ideally, but not necessarily, one will want to extract quickly from the blinded result the unblinded one without having to rerun all the analysis, but this is not crucial. So what do we propose? We propose blinding at the catalog level to act only along the line of sight as not to mess up with angular weights and as making not easy to blind accidentally. And do apply two types of shift combined along the line of sight. One is a geometric Algopaczynski-like shift, and one is a density-dependent Redshift space distortion-like shift. Let's look at the AP-like blinding. As I said, to transform a redshift and angle in distances, one should always assume a fiducial cosmology. So in this step, instead of just taking a fiducial cosmology, we take a fiducial cosmology plus a shifted, blind, unknown shift in the parameters, and then apply the transformation to distances, and then apply the transformation if we want back using the fiducial model to redshift. And then give to the collaboration either the distances or the redshift and give them the fiducial cosmology too. At the moment, this is the important bit that is blind. And this is an example where only the matter density has been shifted, but this can be done with any parameter that drives the background expansion history of the universe. And this has a well model impact on the shift parameters, and we can easily correct a blind alpha into an unblind one the moment one knows what the random seed is, that is what the unknown shift in the parameters is. The second step is a Redshift space distortion-like blinding. Redshift space distortion already distorts the line of sight signal. The magnitude is driven by F, which is unknown. So let's try to mess this up in a controlled but blind way. The idea reminds a lot of reconstruction. Smooth density field solve for the displacement with input growth and bias. Could be an iterative process with FFTs, as already done in the standard analysis. But instead of shifting the galaxies back by the total displacement field, we use only the Redshift space distortion part along the line of sight and add a new F prime to correct the linear growth rate F. in a controlled way. So by doing this, I can even make you believe in modification of GR if I just work by changing this, this exponent. And so this is how it would look like. The shift object by object, it's small, it's tiny. You can see it from the blue to the red points here. But it's a coherent shift on the very large scales that gives a biased reconstructed growth of structure, infer growth of structure. So, okay, so to check if it works, we didn't just check it on a suite of simulations of the data, but also on the actual BOSS DR12 data release. And here are the two analyses, the standard BAO analysis do post-reconstruction and the standard what is called the full shape, where both the information about the baryon acoustic oscillation and the information about growth of structure is included. And here you can see three constraints, the original one, the blue, the blinded one, which is the red, and the corrected one is the blinded one, just corrected without redoing all the analysis, which will give you the blue one. So then a battery of tests has been done. The more important of them is that this operation doesn't change your best fit chi-square in a way that is will make you realize that the catalog has been blinded. So summary of results, we tested this blinded scheme on 400 patchy mocks and on BOSS data to validate that the analytic result agree with the refitted result and that the procedure does not significantly change the error bars. The unblinded parameter constraint can be inferred with enough accuracy prior to rerun the analysis pipeline again on the original catalog, so one can already start writing the paper. So for more information, I put there the reference to the actual publication. So what are the typical questions that I get about this? And I'm gonna just leave them there in case we have to break the ice of the discussion and the Q&A session, and I'll move on. So blending aside, what else can you do? Well, quite a lot actually, but for this talk, and since I don't have a lot of time, let me just add one possibility. Use extra information from different quantities that depend on interesting physics and unknown systematics in different ways. So let me give you an example. There's a lot of ways to play this game. Let me give you an example. What summary statistics do we know? Well, we know the power spectrum, which is the Fourier counterpart of the two-point correlation function. We know of the bispectrum, again, the three-point quantity. And we know of the tri-spectrum, which now I need the 3-dimension to draw it, and not just for the power spectrum and the bispectrum, where I could just do it on the plane of the slide. And this is probably because of the simplex. The triangle is a 2-simplex, that's why it's called bispectrum, and the tri-spectrum is a 3-simplex, so that's why it's called trispectrum. So I would like to concentrate here on the tri-spectrum because the 2-dimensional version was employed in cosmic microwave background analysis and was extremely successful in constraining primordial non-Gaussianity parameters such as FNL and GNL. For the large-scale structure studies in 3D, this has been limited by the difficulty in both measuring this quantity and modeling it. So it was realized very early on, back in a paper by Emiliano Sefusati in 2004, that one would have to define a sort of integrated tri-spectrum because the number of quadrilateral that one can make grows a lot given, you know, a certain number of K modes. So one would have to use an integrated tri-spectrum. The bispectrum has shown to be complementary to the power spectrum, not just in breaking parameter degeneracies, but if modeling assumptions are incorrect, then the parameters inferred from the power spectrum do not agree with those, for example, inferred from the bispectrum. And we learned this the hard way in doing the BOSS analysis. And I expect this to be even more so for the next generation of galaxy surveys. But I would say that the bispectrum is done, and now it's done in quote, because there's a lot more work to be done before this can be applied and give useful results from the next generation survey. But basically the theory, it's there. What has been studied much less is the tri-spectrum. So here's the other paper I want to talk about, Matter Tri-Spectrum, Theoretical Modeling and Comparison to N-Body Simulation. And I would like to highlight the work of Davide Gualdi, who is a postdoc in Barcelona, and Sergi Novell, who was not even a master student at that time, became a master student after submitting the paper. So the zero order issue one finds when talking about the tri-spectrum is how to describe skew quadrilaterals. So a quadrilateral, it's a four-side thing that live on a plane. But in the three-dimensional case, for the tri-spectrum, we have quadrilateral that are folding along the two diagonals, so they don't live in a plane. So the first step is to define a coordinate system. And after spending a lot of time on that, Davide came up with the following way. So a skew quadrilateral is basically given by two triangles, and these two triangles are joined along one of the sides, and they can be folded along this side. So as you can see here. So we need to have a diagonal and a folding angle and a rotation angle. For Redshift space distortion, so we'll also have an extra variable, which is the angle between the diagonal and the line of sight. So after defining this way, it is then possible to define the integrated tri-spectrum. In real space, the integrated tri-spectrum is the sum over different order of the 4K vector, and then again the sum or the integral along the various lengths of the diagonal given the sides of the K vector. So the things can be, and then can be folded also along this diagonal. And in this T, one can put the favorite modeling. In this case, we wrote here in the insert the standard perturbation theory, but one can put whatever one wants. That's for real space. For Redshift space, it's a little bit more complicated because one needs to keep track also of the angle of the diagonal with respect to the line of sight. So here is this mu. Okay, now that's the theory, but in order to measure something, especially say from a simulation or from a survey, typically the density gets pixelized, and then the Fourier transform is done in a fast Fourier transform. So this estimator needs to be discretized. And just to show that we are not faking it, we can write this down, but I will not go here through the equation. You can look at them in the paper and work through it in detail, but we can show that this way it's also unbiased. And remember that for the 4-point function or tri-spectrum, the quantity contains both a connected and unconnected component. In other words, even for a perfectly Gaussian field, while the bispectrum will be zero, the trispectrum will not be zero because of the unconnected components, basically the variance of the power spectrum. So the integrated tri-spectrum estimator, if we are interested in deviation from Gaussianity, be it gravitational, be it because of primordial non-Gaussianity, needs to be obtained by subtracting the connected term. So the unconnected term needs to be modeled and then subtracted to get the unconnected part. Okay, we got it, we can write it down. And for the primordial non-Gaussianity signal, let's take a very simple model, the local type non-Gaussianity, just for show. And then we have the parameter FNL and GNL, and we can work out how these parameters show up in the integrated tri-spectrum. Okay, so can we measure it? Before, let's see what we shall expect. So in this plot, I show the ratio between the local primordial non-Gaussianity component to the summary statistics versus the gravitational signal. So on the top, it's the bispectrum assuming FNL equal 1 divided the gravitational bispectrum. In the bottom part, it's the GNL part divided by gravitational part of the integrated trispectrum, and up here, the FNL part divided by the gravitational part. These numbers in the x-axis are the triangle set or the quadrilateral set. So generally going left to right, one goes to smaller scales, but this is not monotonic because we have to account for all the shapes. So that's why there is this strange structure in this plot. The other thing to notice is that while the ratio between the primordial non-Gaussian part and the gravitational part for the bispectrum goes between 10 to the minus 3 and 10 to the minus 4, for the trispectrum, it's bigger. It's, you know, few 10 to the minus 4, 10 to the minus 3 to 10 to the minus 2. But this somewhat is not unexpected because we know that the primordial skewness compared with the gravitational skewness redshifts away because the gravitational skewness has an extra factor 1 plus z. So we can plot the theory signal. So what did we do for the measurement? We use 5,000 realization of the Quixote suite of dark matter particle simulations for 3 different redshift snapshots and some reasonable K-min and K-max, and assume Poissonian shot noise, which is measured and subtracted from each realization. So what is the upshot of all this? Well, we tried different models, most based on standard perturbation theory, and the error bar reported are for a realization of 1 gigaparsec cube. So the modeling fit well the measurement, but most importantly, we can do a quick Fisher-like forecast because we can estimate the covariance matrix from the 5,000 realization of the simulation. And we find a 30% improvement when adding the integrated trispectrum on the FNL constraint that one will obtain from the bispectrum. So here, the scale-dependent halo bias effect that will be visible even in the power spectrum is not included because the simulation only have dark matter particle for the moment. But this is important because it's still equivalent to doubling the survey volume when trying to constrain FNL, either from the bispectrum or bispectrum plus trispectrum. So my time is up. Let me come to the brief conclusion. As you know, with any technological innovation, there is so-called the Gartner hype cycle. There is some peak of inflated expectation, then there is a trough of disillusionment, and then the slope of enlightenment until the product becomes mature enough and it can become productive. And so at some point, I started worrying that precision cosmology was going toward the same thing. But as in business schools, they teach you, there's a way to go through the trough of disappointment, which is to manage expectation and to accelerate maturity of your product. And I hope I first curb your enthusiasm, if not with the blinding, at least showing a lot of complicated equations in the second part of the talk. But also I hope I presented some tools to accelerate maturity. Thank you.